towards the FTC of plane craft. In this presentation, I want to introduce you to the concept of co-designing a boat geometry with this active control system. And the reason I bring up the F-16 is because that's exactly how the F-16 was actually designed. I'm the new guy, as you can tell, so I'm going to present myself a little bit. I was born and raised in Puerto Rico. Boats have been a long-time passion of mine. Did undergrad and graduate studies in naval architecture at Webb and Michigan, respectively. I did 2 years at NAFC, and now in my new endeavor, I currently Hydrodynamics. Before I start, I want to mention that all these results are actually done while I was at the University of Michigan, and it was done under the supervision of Professor Jingson and Professor Armin Troche. Jingson is controls, Troche is the hydrodynamics. And also, all these results are numerical, therefore to see them more of a qualitatively results rather than quantitative. Plane craft are vessels that I think we all know, but they're essentially the simplest craft you can make very fast. And you can make a boat pretty fast, a table boat there pretty fast, but they've been around for a while as well. Perhaps one of the earliest examples was Turbine in 1894. And even though they've been around for a while, we're constantly trying to improve them. We're trying to improve their drag, we're trying to improve the seakeeping, especially for craft that need to operate in rough conditions, because many times these people get hurt going fast and hitting waves. And there's been many ways to address these metrics, but one of the ways actually has been using control systems, active control systems. And they've been shown to improve these metrics. They've been shown to remove stability problems. When I mean stability here, I mean purposing. And they've been shown to improve seakeeping. And there's been actually some full-scale trials. And one of the samples is Navatech's uplifting body, shown here. But all these experiments have been done in a sequential manner. And what I mean by this is that first the boat was selected, and after you have a boat, you added the control system to it. But because the boat geometry and the control system both interact with each other, a sequential design is not optimal. So here is where co-design comes in. In co-design, we select the parameters of the geometry of the boat and the parameters of the control system that we want to modify. And we explore the design space at the same time, in contrast with the sequential, as we can see here. And co-design is not new. Actually, aerospace has been using co-design for a long time, actually from the very beginning, simply because planes needed to be easy to control by a person, right? Boats don't really go up and down. You know what I mean. But planes do, so you need to be able to control it. But it wasn't really explicitly talked about until the 70s when they started talking about control configured vehicles. And that's when, from that research is where the F-16 came out. And so during my time in Michigan, I tried to answer this question, should we be using co-design for boats with active control system? Because this is the question aerospace asks, and they have implemented it. But we, in the naval field, we really haven't implemented co-design into the equation. And from my results, it looks like yes, we should. It looks like if we use co-design, we could get boats that outperform these sequentially designed boats in calm water drag and seaway drag, seakeeping, and we're talking about all at the same time. And we also pretty much end up with two designs, the controller and the geometry. Here what I'm showing is the perimeter front for one of my investigations. If you're not familiar with perimeter front, a perimeter front is essentially all the best designs you can come up with. There's no designs better than the ones in the perimeter fronts. And we're looking at here two metrics, the seaway drag on the X and the seakeeping metric on the Y. And what you want to take out of here is that the co-design, which is the circles in red, it looks like they all outperform all the sequentially designed boats. And the circles without filling are actually boats that would be porpoising if they did not have a control system on them. So that was an interesting result. And the reason, what I'm trying to show in this slide is the reason why we end up with different boats when we follow a sequential or co-design approach. On black, we have boats with a control system. And on blue, we have the exact same boat without a control system. We have the drag metric and the seakeeping metric both as a function of the trim angle. And as we change the trim angle, we're seeing that the behavior of the two lines is different. So if we're looking at the blue line, we're going to select a different boat than we were looking at the black line. Another interesting result is it looks like there's an optimal trim angle for when you're using a control system in a boat, which is actually a new concept when it comes to boat design, since we all know if we increase the trim angle, we're going to make the seakeeping worse in a normal boat without a control system. Well, then we asked the question of how is this boat going to look like if we try to design it? So this is what we set up to answer by setting a constraint on the seakeeping and selecting a boat from the co-design and the sequential design. And we try to follow conventional scaling rules and weights and centers to see if we can actually design this boat. On the top, well, these are the results. So on the top, we have the sequential design. On the bottom, we have the co-design, and we're also showing a table kind of showing the percent improvements in different sea states. The sequentially designed boat is very conventional. We could probably, we can design this, no problem. Where we see at the co-design, the payload has to be about 3 feet from the transom, which is really not possible to design. Because it looks, in order to match that co-design specification, we need to have a very aft center of gravity to get that trim angle that we need. So from these results, it looks like we have some interesting notes and challenges. The note is, first, the co-design optimal boats look like they will be porpoising with the control system. So we really haven't designed them yet, if these results are true. And two, we will have to come up with new ideas how to design this boat, because we have to put the center of gravity very far aft. An idea that comes up is having a stepped hull that while it's in planing operation, you actually have a dry operating region in stern. And the reason for this is that when you're at 0 speed, you can maintain that 0 trim angle. Because if you didn't have the step, you would just have a very large trim angle when you're at 0 speed. Yeah, and that's my presentation. Thank you.